In this video, we'll build and analyze a table that will contain the mean execution time and confidence intervals when we run a method on an algorithm a given number of times. So we'll modify a little bit the test addition in the sense that we included the name of the method tested as an argument, um, just not to repeat the same name, the construction of the name each time when we call this method. And we created a new method that will print the mean execution time as a table. So we'll receive for this method an array with various numbers representing how many times we execute the algorithm to compute the mean. So in a way representing the sample size that we like to consider in order to compute the mean, and also receive as a constant the max value added. So this will print the timetable for the computing the sum of the first max value added numbers. Now, how we do that? We start by determining the name of the method, then we print the header of the table, and here you just need to think, okay, how big are each of these values and how I want to print them, and compute the number of characters that you want to allocate for each column. Now, this is also trial and error, probably will not um, determine the first time the right sizes, but as you try to run the program, you will see how the table is not looking nice and adjust it to fit the data. And in your homework, you will need to do this each time to increase the table for when the method is slightly adapted. Now, after we put the header, we'll repeat the time analysis for each number of executions that we receive. So we go through the array of executions, and for each number, we call the test addition to and receive a time analysis for that call. And then we print the row in the table with the results. So in the table, we'll have the size, the sample size, so the number of executions that we use, then we'll put the minimum execution time for in this sample, the maximum execution time in this sample, the mean execution time, the value that we are interested in is the mean, but also it will show the confidence interval with 99.9% confidence um, in order to see how sure we are that this is the mean of our population. And after we did all of this, we put the footer for our table to finish the table. Now let's run, and we'll use as execution times. So first, in first sample, we execute 11 times the method. In the next sample, 21. Then we will execute 41 times, 81 times, 101 times, and in the end 1001 times for our method. And we'll add only the first uh, 10 millions numbers. Now, when we execute this, we'll obtain the following results. And sure, you may obtain different results. If I run it again, I may obtain different results. Sometimes some processors, when you do intensive computations, will start to run faster. So many times you will see that your table has some in time and then suddenly drop, and probably your computer will make more sound because it's running faster, and that's normal. So don't worry about it. Sure, our data will be in a way damaged because the setup of the experiment changed. The processor entered in a faster mode, but you may ignore some of the data and consider only when the data when the data is consistent with the given speed of the processor. Now, um, if you look to analyze obtained results, you can see that the mean stayed pretty close to the same value. Even for 11 runs or 1000 runs, the mean was pretty close to the same value. And the only thing that changed actually was the confidence intervals that become smaller and smaller, showing us that we are more um confident on the mean obtained. So we may say, okay, based on this data, 11 execution seems more than enough. Sure, if you try less than 11, always you will get less accurate results. You may, for instance, you see we had a run of 15. If you run only once and the result is 15, sure, the mean will not be 22. Or if you run once and the result is 12, the mean will only be 22. And these are also very small numbers. So being very small numbers, um, these are milliseconds. So there is also an error of the precision of our timer because the numbers are so small. Um, as the execution time will increase for a given algorithm, uh, small differences will no longer count, which is good. Um, Now, again, if you run again this program, you may obtain different means here and maybe 18 here, or as you see, the confidence interval is pretty large, so it's not necessary to get 22. You may get anything as a first value from uh, a smaller value to a large. For instance, from 18 to 26 is very likely you will get another value here. We are lucky to obtain the mean so close. So uh, to be sure that we got the right result, probably executing 41 times, it's a good compromise.